All right, what's up, everybody? Welcome back to another super fun day, reasonably fun day, normal day, of proof, set theory, and logic. Let me get my marker. So today we're going to start it up with a little bit more induction, and then we're going to get into the whole set theory part of proof, set theory, and logic. We're going to start talking about it a little bit. Super fun. People in class who just got the new note packet, people online, you can go get the new note packet online. We'll use that in the second part of today. Fun. So first homework, due date, coming up. Don't forget about it. All right? Good stuff. And yeah, we're basically through chapter 1 and chapter 2 now. That's nice. Through the first set of notes. Pretty cool. Nearing now everything you need for the first exam. So actually, you're a surprising amount of the way through this class. Kind of fun. So yeah, questions about anything before we jump back into induction? Didn't figure there would be, but might as, oh yeah.
So with we've already finished chapter 2. The first test is 1 and 2, right?
Yep. The question was if the first test is 1 and 2, and it is, yes.
So when are we taking a test since we finished that?
It's on the schedule in the syllabus.
We're following the schedule then?
We still are indeed following the schedule at the moment. We may have to adjust. We definitely moved a little bit quicker, which is good. It's certainly not a bad thing. So if you look at our schedule, today is the 19th. We should be doing section 2.2. So it looks like we're actually about 2 days ahead right now, since next week would have us finishing section 2.4 on Wednesday. So that's kind of good. We got a little bit of extra room in there. Nice. Yeah, always good to run a little bit ahead. The exam will be on October 3rd, according to the schedule, and we'll stick to that. So plenty of time to do the first homework and the second homework. Ask any questions you have, study it up, feel ready. We'll do a review day too. Cool, good question. Any other questions? No? Fun. All right, let's do a little bit more induction. So here's another example. These ones aren't in your note packets. I just figured it would be nice to have a little bit of extra practice. So let's prove that the sum from I equals 1 to n of I cubed is equal to n squared times n plus 1 squared over 4 for all positive integers n. Okay, so if we start this out, the whole business will work in exactly the way of the last ones. Our proof will begin with, we proceed by induction. For the base case, now this is not too bad. So you want it for all positive integers n. What's the smallest positive integer n? N equals 1. Yeah, exactly. N equals 1. Let n equal 1. Then the sum from I equals 1 to 1 of I cubed, well, this is just equal to 1. And would you agree that 1 is certainly equal to 1 squared times 1 plus 1 squared over 4? That is, 2 squared is 4. 4 over 4, 1 squared, it's just 1. Yeah? Okay. So the result holds for n equals 1. Now, assume the result is true for some k greater than or equal to 1. Or even just say for k greater than or equal to 1. Yeah, let's just say for some. I don't want to make it sound like I'm saying just like there's just one somewhere. But let's just assume it holds for a value k with k greater than or equal to 1. Yeah? i.e., assume that the sum from I equals 1 to k of I cubed is equal to k squared times k plus 1 squared over 4. We show this implies that the result holds for k plus 1 as well, i.e. that the sum from I equals 1 to k plus 1 of I cubed is equal to, well, it would be k plus 1 squared times k plus 1 squared over 4. Yeah? Observe the following. So we'll start out with what we know. We'll use this piece to get this. We'll take one side of it, we'll perform some manipulations, and we'll produce our desired result by at some point using this fact. Does that make some sense? Hopefully so. It's basically the same structure as some of the other ones we've done. Let's try it out. And also, let's try it out with a hopefully slightly better marker. Everyone keeps taking all of my good markers. They disappear. They just vanish into the ether. Okay, so we'll start by taking the sum from I equals 1 to k plus 1 of I cubed. And we'll notice, what trick are we going to use? What did we do last time we did one of these?
We split the sum.
We did what?
Divided the sum into two parts, right?
Yes, exactly. We break the sum apart. That is, if we're summing from I equals 1 all the way up to k plus 1, we could equivalently write this sum as the sum from I equals 1 to k of I cubed, and then add on the last term. Do you agree with this so far? Okay, cool. Now, via our inductive hypothesis, that is, by our assumption that the sum from I equals 1 to k of I cubed is equal to k squared times k plus 1 squared over 4, we can replace part of this sum with what we've supposed that it's equal to here. So this is k squared times k plus 1 squared over 4 plus k plus 1 cubed. What do you think of this so far? Does this feel reasonable? The trick? Hopefully so. Whenever you're trying to prove something about like a summation or a product or something like that, a formula involving that, and the index up top is where you're, wanting your induction to range over. That's where the variable your induction ranges over lives. Then you split the thing apart. It is always a good idea. Okay, so once we're here, all we have to do now is some algebraic manipulation to turn this into our desired conclusion. K plus 1 squared, k plus 1 plus 1, that'd be k plus 2 squared over 4. Yeah? So let's do it. Let's put it all together. So all we got to do is get a common denominator, and you get a k squared times k plus 1 squared plus 4k plus 1 cubed over 4. Hopefully we all feel good about that. Just get a common denominator. Now let's do a little factoring by grouping. Okay, let's try it out, and we'll get k squared plus 4 times k plus 1, this whole quantity, times k plus 1 squared all over 4. That is, I said, hey, look, I got a k plus 1 squared, and I have a k plus 1 squared hidden inside of this k plus 1 to the third. I just have to factor a k plus 1 out. Does that make some sense? Maybe I'm skipping a step right there and people are not liking it. Basically, I'm just writing this k plus 1 cubed as k plus 1 times k plus 1 squared. Does that make sense? Maybe a little better? Okay. No K? Okay, I don't know. Something there. Okay, So then we just pull out this k plus 1 squared from both terms, and we end up with k squared plus 4 times k plus 1 right there. And now all we have to do to finish it off is just keep going a little bit. This thing is equal now to k squared plus 4k plus 4 times k plus 1 squared over 4. And if we do a little tiny bit of factoring, is this k plus 2, that whole quantity squared, and then a k plus 1 squared over 4? It is. And now just to have good form, let's rewrite it in our desired format. That is, let's write this as k plus 1, that whole quantity squared, times k plus 1 plus 1, that whole quantity squared, all over 4. And now we're done. We started with this, and we showed it is equal to this, the thing that we want. So we should say that we're done to have, a nicely written proof. And we'd say something along the lines of like, so via the principle of mathematical induction, the result holds. That is, our claim is true. It is indeed a true statement. Okay. Maybe? Maybe not? How do you all feel about that? Say I gave you one like this on an exam. What would you do? Would you do okay at it, you think? Some people are giving me a look that says no. And that's okay. You get more practice. We'll do plenty of these on homeworks and, hopefully, well, let's do another one even. How about that? Let's go do one more. Let's see how it goes. So, next board. Let's try this one. Example. Prove the following theorem. Theorem is as follows. I will say it this way. I will say 2 to the n plus 1 is greater than n squared for all positive integers n. Okay, this also resembles one that we've done previously, though perhaps people will find it more difficult or less difficult. Let's see. Give it a shot. Take a moment to try it, and we will see how it all comes together. Okay. How's it going? You making progress? I wrote out a base case in the beginning of what you need to show for the inductive step, if you are still stuck on it. The base case is you just take n equal to 1. You plug it directly in and you say, hey, how about that 4 is bigger than 1? Yeah, okay, we can roll with that. Now, you say, suppose the result holds for some k, with k greater than or equal to 1. That is, suppose that 2 to the k plus 1 is greater than k squared. Now you need to show that this implies the result holds for k plus 1 as well. That is, 2 to the k plus 2 is greater than k plus 1, that whole quantity squared. To do this, you need to do some calculation, and I think this may be where people are getting stuck. Is anyone feeling like they're getting it? Just need a little more time? Okay, I'll give you a moment more. I see some people writing. Okay, I'm still seeing a fair amount of writing, but I'm seeing a lot of people who have paused writing now. Let's try it together. Let's see how far we can get. Who has an idea on how to start? Or what's something someone tried? What do you got?
I took out the plus 1, like to make it 2 times 2 to the k plus 1.
Okay, right on. So you said you started with 2 to the k plus 1, and you noticed that this is equal to 2 times 2 to the k plus 1, right? Okay, and then from this you said, well, we have an assumption about 2 to the k plus 1. We're assuming that that's bigger than k squared, yeah? So you say this up here is greater than 2 times k squared. And what did you do then?
I stopped.
Ah, I see.
Expand k plus 1 squared, right? Be k squared plus 2k plus 1.
Okay, so you're noticing now that k plus 1 squared is k squared plus 2k plus 1. Yeah? Okay, and what do you want to do with that?
We can just like, is it possible to assume that k squared plus k squared is bigger than this quantity here?
Oh, okay, so you're saying something along the lines of you want to make a statement like, okay, well, this thing here, k plus 1 squared is k squared plus 2k plus 1. And so you go, well, hey, we're assuming that k squared is less than 2 to the k plus 1. And so you're going to make some sort of statement like, well, this thing is less than 2 to the k plus 1. And now I have plus 2k plus 1. And are you trying to get some sort of a statement connecting this here and that there? That's a perfectly reasonable thing to do. Build a bridge at each side and try to make it meet in the middle. Okay. Yeah.
How did you go from 2 times 2 to the k plus 1 to k squared?
Ah, so 2 to the k plus 1, by our supposition here, 2 to the k plus 1 is bigger than k squared. They're not equal. Hence this, right? This thing equals this thing, which is bigger than this thing, right? I'm writing it with this like aligned column here instead of like just a super long string of equalities. Is everyone cool with that? Sweet. Okay. So once we're here, we're like, hey, that's k squared. Reasonable. Now, are you trying to get some sort of thing perhaps where you're saying like, look, 2k squared are you trying to do something that's saying like 2k squared is bigger than, say, okay, so you're trying to go for something where you say like 2k squared is bigger than k squared plus 2k plus 1? Is this something like what you're doing? Okay, okay, that's perhaps reasonable. We could try to go through and show that. We could do like a second step of induction on that. Would you like to proceed that way? That's a double induction proof where we do induction, well, not even quite a double induction, but it's an induction where we'd use an induction to prove a subresult to get to the full thing. That's a perfectly reasonable approach. If you'd like to do that, that will get you there, I believe. But is it the only way? Does anyone see any other approaches? Does anyone have any other ideas in their minds?
Logic differently first step.
Would you agree with this? Would you agree if that k is, say, greater than or equal to 1, then k squared is greater than or equal to k? Does that seem reasonable? Okay, perhaps there's something we could do there? What do you think? Maybe using something like that? Okay, we could perhaps turn this into like a, well, let's see, we just need this 2k plus 1 business right here. We're almost there, yeah? We're very, very close. 2k squared and k plus 1 squared. Let's do your idea. There. And let's go off to the side right here for a moment. I'm trying to like lead you through how you might approach a problem like this, without perhaps knowing like some sort of like overarching trick, right? Just like looking at what you've got. Let's just plug and chug. Let's go the way, whatever way seems most convenient. Okay, so over here, we're going to take a moment. We're going to go, okay, we show that, well, we want to show, let's see, we want to show that 2k squared is greater than or equal to k plus 1 squared. Okay. I'll say for all integers k greater than or equal to 1. We do so via induction. For the base case, let k be equal to 1. Then, 2 times 1 squared, would you agree? I'll write it this way. Then, 2 is certainly equal to 2 times 1 squared. And wait a second. Is this going to be true? Is this greater than or equal to 1 plus 1 squared? Uh-oh. Oh no. So we need to take a step back, right? Okay. So we have to take a step back here. Let's move backwards a moment. Actually, let me make sure. Is this? This will be fine. Okay, so let me look at this for a moment. I did not actually write down my solution or like a proof for this last time. I just grabbed a few more extra induction proofs. So let me make sure I won't lead you on any unfortunate journeys real quickly by double checking in my mind that this is actually true and perhaps I didn't copy something down wrong. N plus 1 n squared. I believe this. This is true, yeah. Oh, okay, here, I know what we can do. We, yeah, okay. So, okay, I think I know what to do, but I am hopeful that I don't lead you on a wild goose chase right here. I may, we'll find out. If it ends up being any sort of problem, then we'll just skip over it and we'll do it next time really fast or something like that. But I'm pretty sure I remember how to do this right. So, now that we've got this here, we have a couple of different options. One, we could try to do what someone did before, where we said, hey, can we somehow show that this is bigger than what we want? We just went through and we said, does this make sense? If we take k equal to, say, 1, this would just be 2. Well, on the other hand, k plus 1 squared would be 4. So it seems like maybe there's something bad going on here. Yeah? Now, we need to be a little bit careful. Something is throwing me here. Did I write something weird? I haven't written anything wrong, I believe. K squared plus 2k plus 1. K squared. Yes?
I'm trying to show that 2k squared is greater than k plus 1 squared when we're trying to show that it's 2 to the k if that's bigger. I don't know if that makes sense, I guess.
Oh, I think I see what you're saying. Yeah, okay. So the idea is that we have this piece right here that says 2 to the k plus 1 is bigger than k squared. Yeah? Now, we start with one side of what we want to show, and we should produce an inequality giving us the other side, right? Like that is, we start with this, we carry out manipulations, and hopefully we show that this thing is indeed bigger than that, right? So we start with one side of it. We go, I've got 2 to the k plus 1, and I try to do some basic algebra. I pull out a 2, and then I've got my 2 to the k plus 1. That is something I know something about. 2 to the k plus 1 is indeed greater than k squared, right? We've shown that. Okay, so then I get, this is bigger than 2 times k squared. That's good. Okay, now we need to somehow produce k plus 1 squared over here. This is the tricky piece. Does anyone see a trick?
Should be a trick.
Okay. See, I could have played it like I knew, and I was like, think on it till next time. But I don't want to lead you down any rabbit holes in case the idea I have in my head doesn't actually end up working out. I don't want anyone to be any more confused. So think about this one for next time, and we'll do it at the start of class next time. A good, tricky induction argument. I will make sure that the idea I have about it ends up working right, and then we will do it together. It's a good one to think on for the moment. Fun, Friday, all right. Cool. Instead, let's take a step back and move on from induction into chapter 3 and begin to talk about set theory. Cool. We can take this as a moment to reflect on why it's, good for me to actually make sure I write down all of the things beforehand, especially if I know that last time in class I was like, oh yeah, this is an easy one, I can do this. And then now I want to make sure that I don't mess anything up. Always a joy when that happens. All right, so set theory. What's it all about? Sets, what are these guys? What's going on in set theory? Well, what's a set? That's the first question. So there is a naive approach to set theory, and there is a more nuanced approach to set theory that is better. And we will start by talking about the naive notion of sets that people originally began with. So in chapter 3, which is all about set theory, we will start by discussing what is a set? So, here's the idea. At first, the correct idea for a set seemed to be something like a collection of objects. That is, on some sort of level, people are like, oh, a set, it's just, some sort of collection of things. Okay, seems reasonable to say. And people started by supposing that we supposed that it was enough to have a rule to clearly specify what can belong to the collection, i.e., that sets could be defined in a reasonable way by, or I'll say defined at defined with predicates. I'll say with instead of by. With predicates by aggregating the members of the specified universe that satisfy it. I.e., if you have some sort of a predicate, you would say something like, okay, we'll take all this, here's like all of our possibilities, and we'll say, okay, we'll make a set. It's the stuff that satisfies this predicate. Cool. Seems reasonable, right? Like the set of all students in this class who are wearing black today. Okay, there you go. That seems like a reasonable set to talk about. There are problems, actually. You may not think that there would be problems from this, and indeed, people probably were like, yeah, that seems reasonable, right? There are problems with this, actually. We have to be a little bit more careful. So, our sense of what a set is, and this is how you can think of it, is a set is a big bag of stuff, all right? It doesn't matter what order the stuff's in. It just tells you, do you have the stuff in the bag or not, right? It's not like a nicely organized collection of things. It's just some stuff. Things are either in the set or they aren't. Okay, easy, great. It's a collection of things. You can come up with some easy notation for it. What we'll use is we'll use curly braces to denote sets. Okay. The issue begins to come up with when you try to talk about sets in terms of predicates, basically. That is, if you try to make some sort of a statement where you're like, hey, the set of all things in this universe that satisfy this property, you can quickly run into some problems when our universe is the collection of sets. Here is a kind of classic example to it. Here's like an old school version of it. So this leads to some issues. Namely, basically, I'll give you the old school version of what it is. Here's the idea of what the issue is. This is an old, I guess I could say riddle or paradox, perhaps. If the barber shaves every man who does not shave himself, who shaves the barber? Uh-oh, yeah. The right answer is that the barber is a woman. I don't know, right? Who knows what the actual, thing of it is. But this is like this is this is a silly analog to a real issue. That is, if we are trying to talk about what all the sets are, and we aren't exactly clear about what things are or aren't sets, if we suppose that things could, sets can be defined as objects satisfying a predicate, like in this sort of a way, all of the things belonging to, universe such that predicate is true, we kind of run into an issue as soon as we use this as our definition, because once we do this, if we start to make sets by referencing the sets that satisfy things, what if you take, for instance, the set of all sets that do not contain themselves? Think about that. That's basically the same as the barber paradox, right? If the set is in it, well, then it shouldn't be in there. But if it's not in there, then it should. Uh-oh. Oh, no. These kind of self-referential statements can really quickly become a problem. And this guy named Russell, Russell's paradox, as you may have heard of it before, came up basically with an issue, with a paradox that was like, look, you can't do this, actually. There are limitations and problems. We will talk about this more later. But it's worthwhile to think about sets from the get-go as something perhaps slightly different from just collections of things that satisfy a condition. That is, when you're talking about sets, if you can clearly specify what is in the set by actually listing the things out, that is great. But if you can't, you should take great care to make sure that you are not making some of these tricky kind of self-referential statements, because there are problems that can come up. We will revisit this further on in the class, but it is a worthwhile thing to mention from the get-go that our initial kind of naive way of dealing with sets is perhaps not appropriate for all things but the very smallest of sets, the most concrete and easily accessible sets. Okay, so maybe we should, before jumping into all of these sorts of paradoxes and issues that can come up, start to talk about, well, what the heck are sets? Let's get some examples. Let's get our hands on them. Let's get some concrete idea of what a set looks like and some notation for how to write them before we start discussing the paradoxes that come up, since we'll need some machinery to actually be able to write them in a meaningful way instead of me just kind of blathering about potential problems or something like that. So this brings us into, since section 3.1 is extremely short, the elements and subsets of a set. So our notation will work like this. A set is a collection of objects called its elements. So the things in a set, we'll call them the elements of the set. And so far, notice I've just left this extremely vague, right? Like objects, like what objects? I don't know, whatever ones you want, right? You could have a set that has me, you, the integer 3, a picture of a train, whatever you want. Put anything in a set. A set is just a collection of things. Okay, so the objects can be anything, right? Now, many times you want to restrict what the objects are, so you're not just talking about absolutely everything. But intuitively, you could take a set that, it's got stuff in it, right? Who cares what the stuff is? It's a collection of stuff. All right. So they can be anything. Okay. For a set to be well defined, we need to be able to say if something is in it. So if something is one of its elements. All right, we'll have some way to do this. And we'll perhaps need to talk about when the sets are the same. So we'll say that two sets are the same, and I will erase this board and switch camera over to the next, when they have exactly the same elements. All right, I know this is all a little bit hand-wavy at this point. Let me introduce some notation just an instant later. But I think that just kind of the casual way of initially talking about sets makes any of the baroqueness of the formalism feel more approachable. Sets are really simple little things, at least the concrete ones that we can get our hands on easily, just, in examples and stuff like this at the start of class. They are just collections of stuff. You can put any old thing you want in them. All you have to do is have some way to write whether or not a thing belongs to a set, and then you have some way of describing equality of sets automatically from that. You could just say they have the same elements. So, stupid little pull. We say two sets are equal if they have the same elements. Now, here's the idea, the notation. We use the open and close curly brackets to denote a set and write its elements as a comma separated. Does comma have two M's? Yeah. It does. Okay, yeah. List. Okay. So, example. A equals, say, 1, 2, 4, and 8 is a set. B 8, 2, 1, 4 is a set. C 1, 2, 1, 4, 8. That's a set. D, here's another set. 1, 2, 3, 4, and 8, also a set. Here, A, B, C, and D are all sets. A and B have exactly the same elements, don't they? I've written them in different order, but sets don't have an order. They are not like ordered pairs. They don't have like the first slot and the second slot. They are a bag of stuff. You have a bag of stuff and you shake it around, you still have the same stuff in the bag, yeah? Maybe it's broken now, but you have the same stuff. Okay. A is indeed equal to B. And what about C? Some people say it's not equal. Why would you say it's not equal? There's two ones. Okay, and this is a great question. So, how we tend to do it, and I believe that when you say they're not equal because there's two ones, what you're thinking is that these ones are somehow distinct. There's a perfectly reasonable way of trying to come up with a way to formalize that there could be two distinct ones, right? But as we tend to do it, we would assume that without some sort of additional language or specification of the things being distinct, that this is, it's written with the same digit, it's the same thing, right? So they would indeed be equal. They have the same elements, right? Is 1 in A? Yes. Is 1 in C? Yes. Is 2 in A? Yes. Is 2 in C? Yes. Is 4 in A? Yes. Is 4 in C? Yes. Is 8 in A? Yes. Is 8 in C? Yes. Is there any element that belongs to A that does not belong to C? No. Is there any element that belongs to C that does not belong to A? No. They have the same elements. So indeed, A is equal to B and is equal to C as they have the same elements. D, however, is not equal to A, B, or C, right? Since 3 is an element of D, but is not an element of the other ones. Yeah? Okay. Since 3 is an element of D and is not an element of A, B, or C, D is not equal to A, B, or C. All right, they are distinct sets. Cool. I'm using integers to put in these sets, but there's no reason you couldn't put other things in there. You could put all sorts of stuff in there. Now, I've noticed that we're writing 3 is an element of D and is not an element of A, B, or C. I don't want to have to constantly write is an element of or is not an element of. Let's make a cool symbol for it. Yeah? Notation. Write X is in A if X is an element of A, and write X is not in A if it is not. That is, we have this little symbol. I'll draw it all big. Looks like this. Kind of like a weird little E. I don't know why. It's just so when we talk about some of the other notation, I think you'll see where this kind of like the idea of how it comes in. But you can just assume it is like a random symbol we've picked to mean in, right? The symbol doesn't matter so much. The symbol is just a way of denoting is an element of without having to write so much stuff. Yeah? So it's like a little E, but notice it's not like a little like this. It's not like a little like epsilon or something like this. How it is written is like a little cup with a bar in it. So some other notation that we will bring up now is subsets. Subsets, and hopefully by bringing up the notion of a subset, I can make this notation a little bit more clear. Here's the gist of it. So subsets, and I'm slightly jumping ahead in the note packet, skipping one example that we will come back to in just a moment. But subsets work as follows. So a quick definition. Given two sets, A and B, we say that A is a subset of B if every element of A is also an element of B. We write A is contained in B to denote this. Now, a couple of notational pieces. Actually, we're getting to the very end. I bring this up mainly because of the notation piece right here, and this is a good spot to end, since then we'll have some notation to go through next time to talk about things more clearly. When you write this like sideways little cup thing, notice it looks like the sideways little cup thing you use with the in, yeah? Some people will just write it like this to mean this thing is that. A lot of times people put the line underneath to mean that it is contained within, or perhaps even equal to. And the idea of using the sideways cup with the line inside of it to mean element of well, I guess kind of makes obvious sense. It's like containment, but instead it's inside of, I guess. So you can see a little bit of the uniformity in the symbols there. But yeah, subsets. Little set could be the same thing as the bigger set, but every element in A is also an element of B. Okay, cool. We'll talk about subsets. We'll do more stuff with sets. We'll do lots more examples. I'll also finish that induction proof that I glamorously failed at the beginning of class. We'll see you after a nice weekend. Have a good one.
Thank you.